All right, hello everyone. My name is Goku Jess, and this channel is it's a way for me to teach myself and honestly connect with subjects and crazy concepts more because I believe that when people teach others or they try to explain concepts in verbal form, visual form, I think it just helps cement that connection between concepts that are sometimes difficult to grasp in life. So this isn't just physics. I know the tab's labeled physics, but I mean I'll come here with math, calculus, just a way for me to teach myself, and hopefully if you need to teach yourself as well. um a bit about myself is that well, I don't give too much away, but I am a student. I'm a senior right now, gonna go to college here in Florida. Gators, let's go. And well, this is just a way for me to help other seniors or anyone who just wants to learn, um, just to understand concepts and grasp them a little more, because it can be tough as a teacher to try and connect with students because you know the content, you understand it, and it's hard to relay that understanding to others. So in my head, I don't really understand it, and maybe you don't understand it, and that's a good thing. So we can just figure it out by ourselves. And if I'm ever wrong, please comment. I'm not really that. I don't want to sound too. I don't want any. I don't want to showcase false humility, but I don't think I'm a very intelligent person, but I just think I just want to learn and get better, and hopefully that's the same for all you. Okay, so let's start. So today, not today in class, but in my E&M class, we learned something called Coulombs Law, which I definitely butchered the spelling. I don't know though, but we'll see. Coulombs Law, right? No, I don't like the way that is. But what the Coulombs Law is, it's kind of the same idea that I want to say the law of gravity have, right? So what is the law of gravity, right? We know that the law of gravity, or the force of gravity, is this equation right here. It's m1 times m2 times the universal gravity constant g over r squared, which is the separation distance between two centers of mass, and that's what it is, right? So this is the distance. Let me just distance of separation between two objects center of mass. Also, I just want to reiterate a tip that I think helped me a lot is don't try and write everything I say if you are taking notes, of course. But I think a great way to do it is what I did was I like to paraphrase myself. Take what my teacher said and just spit it in my own words, and don't write everything he puts down. If you write everything he puts down, it's just a bunch of jibber jabber. Well, for my experience at least. I don't know how you guys like to write your notes. It's just a tip. Hopefully that might help others. But this is the separation between the two objects. These are the two masses, right? Two masses in any space at any point in time. And this is the universal gravity constant, right? And I think a great way for me is make sure we understand the units, right? We have kg squared over meter squared, and this would be in newtons, right? So the gravity constant, if we want to get it to equal to newtons, it has to be in m squared kg squared times newtons. All right, so when I have this in here, I cancel out this newton with this kg squared with this kg squared, this m squared with this m squared, and then we have newtons left. So that's what the gravity constant is. So let's go on to Coulomb's law. And the reason why I brought up the law of gravity, or the force of gravity in this equation, is because Coulomb's law is actually highly similar and showcases a very similar relationship to the gravity law, right? So this is what Coulomb's law is, right? Q1, Q2 times K over R squared, right? So let's break down what these are, and I'll explain to them as we go, right? This is the Coulomb constant, right? I think that's the name. If I'm wrong, please tell me. Coulomb's constant, and this is the same thing as r squared, just a little smaller, just to showcase it's a difference. It's actually it's the separation distance, but instead of two objects center of mass, it's the two objects center of charge. With Coulombs Law, we're dealing with charge. I probably didn't mention this, but right now what we're dealing with is electrostatics, right? And what we're dealing with is charge. Charged particles. Charged particles called electrons, or E, right? And we have two different particles. We have E minus and E plus. And I'm guessing you guys know what E plus is, but if you don't, it's the proton, right? So in atom, this is not at all what in real atom is, or does not travel in orbits whatsoever. It travels in more of a cloud, of course. But basically, let's say there's an atom here. Pretend this is an electron, right? It's an E minus charge, and a proton has an E plus charge, right? This is just how we just show what it is. And what it is that this is a proton and this is an electron. So actually the problem with electrostatics was when it was created, this was according to my teacher, Mr. Shelton, is, of course, when we found out these kinds of relationships and we saw it, we didn't know which charges were actually flowing. It actually was very recently discovered that it's only the electrons that flow. Again, I want to iterate that. If I'm wrong, please tell me, because I could be totally just like BSing. But I think that's what my teacher was explaining, that the reason why it's a little confusing is because we know now that protons are not what allow for the flow of electricity. It's the flow of electrons that, contribute to electricity, and protons actually just stay in their nucleus, right? They don't get stripped off unless, of course, we're dealing with nuclear energy, but in this case, we just have electrons that flow. And that's why what we have here is Q1 and Q2. These are actually charges, right? You have a charge 1 and charge 2. And a big misunderstanding that a lot of students have, well, in my class at least, is that, well, since charges can be negative, does that mean the force is negative? Well, that's the thing about physics, right? When we say something is negative, usually what we're referring to is, of course, what we're referring to is is direction, right? So for example, what these negative and positives tell us, they don't tell us that the quantity of the force is negative, or you have to add it, or that the actual force is negative per se itself, because how can a force be negative, right? Let's say you just actually take a gravity force equation, right? And you calculate the force of gravity between Earth and the sun. You can't calculate that. You can't find a number that's negative, right? So what it actually is it's the beauty of physics, in my opinion, because I love this. I struggled with this subject when I was first in mechanics, of course. I was so confused, but basically the idea is, right, all these constructs we have for direction and coordinate systems, they're all false. And if you're watching this, you probably, and you've taken physics before, you understand that, right? So let's say I have a number line, right, from 0, where we have this standard equation that's this is 0, this is 1, this is 2, this is 3, this is -1, right, -2. But the idea is I can shift this wherever I want, right? I know that this way you're moving in the positive direction, right? Because as you go this way, even if you started from -2 and you go this way, you are moving in a positive direction. But if you go this way, you're going to go in a negative direction, right? So the idea is, right, we know how magnets are, right? Magnets have, say I have a magnet right here and a magnet right here. And this is the north side, this is the south side, this is the north side, this is the south side. Sorry, this is, just for the demonstration, this is the south side, this is the north side. What's going to happen, right? We know that as kids that when we have magnets, we notice that with one side, they attract, right? This is going to come this way, and this is also going to come this way, right? But if you had the same side, it's a force of repulsion, right? We repel. This goes this way, this goes this way. And that's the thing with Coulombs Law that differs from the gravity. The gravity equation is, if you place two objects in space, right, they're never going to repel each other unless another force acted on them. We're just assuming here that it's just a force of gravity, right? Let's say I had the moon here and the earth here, right? This is the moon, this is the earth. Horrible drawings, of course, but again, just to show you, right? They will never have a force of repulsion if the force of gravity is the only one acting. Force of gravity is it's a attractive force. It always will be, right? That this will never be negative unless we define direction. And direction is a very key part of this because you need to understand which way the force is going, right? Because in this way, right, let's say I had, which way would this charge be moving? It would be moving this way because this charge is positive. But if this charge was, negative and this side was positive, then the force would pull this way, right? And you see how we have direction here? Direction here is arrows. So we know this way is actually the negative direction, and this way is the positive direction. So although these are negative charges, right? So you have negative q times q, you would get a negative q squared. That's not what we're dealing with here at all, right? Even though that this is we're not dealing with the magnitude of, we're not. The reason why we put these negatives and positives here is we're indicating that the force of Coulomb's law is a vector, right? It has a direction. And that's something that a lot of students aren't very comfortable with at first if they don't understand what vectors are, right? Vectors are units that have direction, and that's what this force of Coulomb's law, the Coulomb's law is. It has a force of direction, right? So right now what I'm doing is I'm just breaking it down to the basics, the simplest. It's for my brain to understand, and if you don't understand, I'm so sorry. Again, this is the first time doing it, so hopefully it'll work. But yeah, basically that's what it is. So you know what? Let's clean this all up, right? I'm just gonna clean this all up. We don't need the gravity. We understand it, right? Hopefully we do. And let's just get down to the nitty gritty stuff right here, right? So, force of Coulomb's law, right? This is equal to Q1 times Q2 times K over R squared. Q1 times Q2 times K over R squared, right? We know that charges can be negative, right? They have a negative charge or a positive charge, right? You have a charge, let's say this is a negative with a magnitude of Q, and this is a positive Q, right? But we always have to establish direction first. Always, always, always. This is the key thing. Establish your coordinate systems. Establish everything. That's the beauty of physics. You can make up anything you want. It's all construct. It's arbitrary. It doesn't matter where you say it's negative. I could say this is positive. This is negative. I could say this is negative. This is positive. I could put my 0 here, I could put my 0 here. It doesn't matter at all whatsoever as long as you just keep it consistent. Just keep it consistent and everything will be fine. But for this case, I'm just going to do it like what everyone else does. And the right is positive, left is negative. That's what we're going to say, right? So let's say this was a negative Q and this was a positive Q. Like a magnitude of charge of Q. And when I mean magnitude, I mean, how do I explain this? Magnitude just means the size of the force itself, not the direction it has. So it could go this way and not go this way, but it could be negative, it could be positive, but it will still remain Q, right? And these have the same Q. So how would we write this in the force equation itself? But what is the force telling us? That's the main thing. I think students like me had a hard time understanding. It's the same thing when it came to gravity. What does that really mean? What it means is the force tells you, what the force tells you is how this charge is impacting this charge, and vice versa, how this charge impacts this charge. So we're going to say a question that a lot of tests have, AP exam would have, is what is the force acting on the positive charge Q? Right? Well, the positive charge Q is going to have a force in this direction, right? Because this is a force of attraction. So if it's a force of attraction, which means, this would want to go this way, right? The charge would want to go towards the negative charge. Same way a negative magnet want to go to a positive magnet side. So it's this way. But we also establish in the direction that this is negative. So we're going to assume this is negative. Right? So we're going to assume the force is negative. This is a negative force. Coulomb's law, right? So let's write it out, right? So But don't put the negative in front. That's not what we're trying to do right now. I'm sorry about that. I should have explained that more clearly. But let's just write what the force of Coulomb's law is. What is this force acting upon it? Right, so we have we have Q squared times K over separation distance of R. Wow, it is hard teaching because I'm trying to break down a concept that I don't even understand fully. Okay, this is what we have, right? And we know that it's in the negative direction. Not because this is negative, this is negative, and they multiply together, it'd be a negative, right? That's not what the point is. Because right now, I could change this and say this is positive, and this is positive and this is negative, right? So this force would still be positive. You don't multiply, when you're multiplying the charges, don't multiply it by the charge it has, right? The positive or the negative. Multiply it by the magnitude of it. The charge is only there simply to indicate direction. I want you to, that's a very important note. The negative, the signs only indicate direction. That is the only job they have. They indicate the direction, only indicate direction in which the force would be acted upon. But that doesn't mean that it doesn't have, it doesn't have a negative charge. I mean, this could be an electron, this could be a proton. I mean, honestly, we never know. Well, in this case, we're assuming we don't know, right? Because when this law came up, we never knew if it was positive or negative particles charged. We never knew if it was positive or negative charged particles moving through, right? We just assumed that it could be both. But now, as we know, we figured out that it's only the electrons that move. But right now, indicate that signs only indicate direction in which the force acts upon. So let's say I want to know, then if the force is this way, what would be the force on this way? Well, let's think about it, right? You could calculate it, but I mean, it's going to be the same exact force. It's going to be the same exact. Think about it. If I said this was particle 1, particle 2, and I said the force of Coulomb's law from the Coulomb's, what is the force from particle 1, the force of particle 1 acting on particle 2, I'll write it like this, force is equal to Q squared K over R squared. Okay, well then what's the force of particle 2 acting on particle 1? It'd be the same exact thing. Squared K over, it's the same exact thing, right? Because if I said I was just looking at this dot only, like it was a free body diagram, I was looking at this dot, this charged particle only, well, which way would the force be going? Boom, this way. It's the same force. It's the same thing. It's Newton's third law. Every action is an equal and opposite reaction. And it's the same idea with gravity, right? Let's say I had Earth, right? People tend to assume that, it's not going to have anything, but it's the same exact. If people say, this is gravity, this is the Earth, and this is the moon, right? And then we'll say this is R, and this is M of E times M of M, right? Well, then what's the force acting on ME due to MM? It's the same exact force acting on MM due to ME. It's the same exact, right? Because if you write it, right, force of gravity. Sorry, I am derailing, and I'm definitely going way, way away from electrostatics, but I just want to make sure, I understand and you understand that the idea of forces is we're dealing with one particle at a time. We're dealing with one object at a time. We're dealing with one thing at a time. We can have dynamic situations where we add multiple particles, but when we deal with forces, we take things one-dimensionally. One thing at a time, one thing at a time, one thing at a time. So right now, we're only taking two things at a time right now and basing it off of this idea. We're pretending this is my dot product. Which way is the force? It's going to be this way. This is my dot product. This is my Earth. Dang it, my Apple Pencil battery's low, whatever. It's my Earth, and which way is the force acting on? Boom, that way it's going to be R squared. That's how it is. It's the same concept, relationship, and idea that deals with Coulombs law. And it's the Coulombs law is actually the most basic thing. We have to learn about this law before I get into Gauss's law, which is Honestly, one of the most confusing laws I've ever endured in my life. But when it clicked today or yesterday, it was immaculate. Sorry, I'm rambling and venting, but yes. So what we're doing here with is the signs indicate direction only, right? From force 1 to 2, force from 2 to 1, they're the same exact force acting on each other, right? One force going this way, one force going this way, but the same force. It's the same force. Okay, that's cool, but now, here's what the AP exam is going to ask you, right? They like to structure their exams the same way. What they want to do is, let's change the scenario up, right? Let's say these two were both positive. Now, what would be the changing? I'm going to ask you a question. What do you think is going to change? Do you think the magnitude of the force is going to change, the direction of the force is going to change, or both? Okay, if you said both, I don't think you understand me yet. If you said the magnitude, I also don't think you understand, because why would the magnitude change? Right, because I didn't change anything. It is the direction. Only the direction would change. Because the magnitude, right? Nothing changes. The only thing I changed was this is positive and this is positive. So what does that indicate is? The directions change. Now, if I made this 2Q, then yes, both the force and the direction will change, but I didn't. Right? And we're going to get into some crazy problems with dealing with each other, right? Okay. So what would the force be here? Well, the force, actually, I don't know why I'm writing that, because the force is the exact same. But all we know is that this goes in the positive direction. This goes in the negative direction. Or, since this is negative direction, this is positive direction. But let's say I'm just looking at this. What is the force acting on? So if you want to draw a free body diagram, and I think free body diagrams, my teacher doesn't like to use them a lot. We've skipped that phase, but I think it's actually very crucial in understanding, the dimensions and the aspects of each problem situation. I think it simplifies it down. I encourage people to do it. I think it's a great way to do it. It helps you break down a problem and figure out where to go from there. So we know that one force acts this way. For we'll say this is 2, right? And then for, let's say, 1, what would be the free diagram in charge 1? Well, we know a force is coming from that charge from 2 this way, from 2 this way. So it would have to be in this direction. Right? And it's the same exact thing. Okay, this is the easy, basic stuff. AP exam's not going to ask us about this. Well, it will, but it's going to ask about it in a lot more confusing constructs, right? What they're going to deal with you is, actually, I do need that definition right there, that formula. Let's say hypothetically, I did a crazy problem. Let's say I had 2 of them, right? 2 here, 2 here, 3. All right, we're going to do this 1, 2, 3. They're all charged Q, but only this is negative, this is positive, and this is negative. You're going to soon later find out that when dealing with electric fields, which is, it comes directly from Coulombs Law, dealing with electric fields or dealing with, honestly, the magnitude of force at a certain place, whatever the charge is here doesn't matter. I could put a charge, actually, I'll explain why it doesn't matter after I do the problem. I keep doing it really hard, but I'll explain why. So let's say this was, what do I want to make this? Let's make it positive. Doesn't matter, right? This is a distance r. Say this is 2/3 r, just to make the problem a little bit cooler. And this is 2/5 r, actually, because it's 5. 2/5 r and 2/3 r. So automatically, I'm not going to even ask about direction or the size. Automatically, what do you think is going to be the larger force, right? Don't worry about the direction, right? When we deal with direction, don't worry about the signs. Sorry, I shouldn't say don't worry about direction. I say don't worry about the signs when I'm asking you this question. All I'm asking for you is, which one do you think is going to be larger charge? Larger force. Larger net force. right? Is it going to be the force from 1 to 2, or from 3 to 2, or from 3 to 1? Well, it's going to be from 1 to 2, right? Because it's, when we look at R, right, this is 2F, R, you know what, instead of R, just, I don't want to confuse people, we're going to make this D. We're going to make this D, we're going to make this D, this is my distance, So this entire thing is D, and this is just 2/5 D, this 3/5 D, right? When we're dealing with distance, what do we know? As you increase the distance, you increase R, you decrease the value of the magnitude. The magnitude of the Coulombs law. But if you decrease distance, R, you increase magnitude. Same thing with gravity, right? If the Earth was settling closer to the moon, right, what would we see? We would see that the moon, would have a way greater effect on tides. And also, maybe bits and pieces of the moon would come off and come to Earth. Because we know that the same force is acting between both those objects, provided we're assuming the sun is really, really far away. Again, there's so many other planets affecting gravity, but right now we're just looking at the Earth and the moon. So we would see that parts of the moon would fly off the Earth, and we would see that the moon would pull on the tides. Why? Because they both experience the same force. It's just the gravity force. It's the same force acting upon each other. And it's the same thing here. I completely lost. Oh, sorry. No, I didn't. I know where I am. When we have a charge that's closer to this one, the force grows by a factor of a square. It says R squared. If I did 1/2 of this, if I did 1/2, if I did 1/5 D, right? If I did 1/5 D, the value of the force would go up by 25. A magnitude of 25 times the force originally. If I did 1/10, 100 times. Did 1/100th, it would be, that would be 10,000 times. Like it's insane how how fast that rate of the force would increase as the distance decreases. So yes, right now it would be 1 to 2 would have the largest force. So what we have to do is, in this thing, what do you think we have to do? Right, what I'm asking for is, I want you to find me the force, the net force, right? Remember this from net force on charge 1, charge 2, and charge 3. And it's not that hard. We could do it, right? So we break this down into free body diagrams. We know that this is my 1 right here, right? We know that there's a charge, there's a force from charge 2 acting which direction? It would act in this direction, right? Charge 2 acting in this direction. And we also know there's a force of charge 3 acting in this direction. But which one do you think is larger? It's going to be 2, right? It's closer. So 3 is going to be a little less, right? So I like to name my attributes, my components of this force. Right? We're going to call this force 2 and force 3. Provided that these are all, it's just the Coulombs force, right? It's just the Coulombs force. So now all we have to do is add up. Ooh. If I was in a class, someone would catch me. But first we have to do is establish direction. Always establish direction. Which one's positive, which one's negative? Positive, this way is negative. Right? So let's go. Let's just do the problem, see where we get, right? So we know that force 2 is equal to Q. How do I want to do this? Let's do force 2 is equal to Q1 times Q3 times K over, and what's the distance between these two? Well, we know it's just D, right? So D squared. That's force of 2. Oh, sorry. That's force of 3. Now let's see what force of 2 is equal to. We know that it's charge Q1 times Q2. Again, these are all the same. I just want to emphasize that these are two different charges. Two different charges by saying like this, 1, 2. They're all the same magnitude, the same value of charge. And we'll see what the thing is. Let's see how far apart they are. 2/5, right? 2/5 D squared, right? Which is equal to 2/5 D squared. That's 25 tenths times Q1 times Q2K over T squared, right? And these are all the same. So I'm just going to get rid of these 1, 2, 1, 3. They were just there to emphasize that, you know, I'm taking this charge, and I'm taking this charge, and I'm trying to find the force based on this charge. This charge is on. Besides, it's going to be like that, right? And all we have to do is add these together, right? This is 10 divided by 10. And we have to add these together, right? Or we subtract them, right? Because the force is negative. Right? Because this is going to be negative. It's in the negative direction. So negative x, positive x. So it's going to be negative 2, negative 2. So the force itself is negative 35 over 10 Q squared K over D squared. But again, what we're looking at is not the direction itself. This negative is not that important as you want to put an emphasis on it. I know that it's there. It looks like it's important. Negatives, right? You always mess up with the addition or subtraction. It's just there to identify direction and know if we're going to be adding forces or subtracting forces. That's all it's there for. Honestly, I think that's a good lesson on Coulombs Law. There's some really tough problems, right? You have a problem like this. I think, you know what? This might sum it up for everybody. This might actually help people understand. This is what helped me understand exactly what it is, right? Take it from here. Let's say I had a charge of Q here. Again, it doesn't really matter what charge is there, but I'll explain why, right? Okay, the force would matter based on what charge is there, but honestly, it really doesn't. But just for the sake, I'll say so. This is positive Q, right? So now let's say, and it's in the middle of the square. It's a horrible square. Actually, I have a freaking square feature. I don't know why I don't use it. I have a square feature. This thing, like, it's like magic. It just aligns the shape. This is not an ad, but it just aligns the shape beautifully. And we got a little cook on it, so that's kind of cool. Okay, so let's say we had, these are our charges, right? We have Q, both positive, and Q, both negative. In which arrangement on these corners, right, would I generate a force of 0 on Q? The net force would be 0 on Q. What does that mean, essentially? Like, no matter how I arrange all these charges on these corners, this Q would not move. There's no force on it. It wouldn't even. It would be a net force of 0 because all the other forces from the other charges just lined up to be 0. So let's try a couple of different arrangements, right? Let's say we had plus Q here, plus Q here, minus Q there, minus Q there. So a way I tackled this problem. No, frick, I gave you the answer. It's actually not that. It's going to be this. Actually, no, I didn't give you the answer. I actually gave you the opposite of the answer. So the way I tackle this problem, right, is I looked at each force and I drew, I think it's a great way. It's a great way to understand. Again, do your free body diagrams. I don't care what professor you have, your teacher have. It's a great way to organize your thoughts and your forces. And you probably will be solving force. That's a big thing about Newton's law. It's crazy. Any problem can be solved with force. Sorry, I thought I could. So here's how we're going to do this, right? We're going to have, I'm going to use, so there's going to be a charge from this Q on this Q, and what direction do you think it's going to be? It's hard to establish direction in this case, right? I can't just say X is positive and Y is negative. Why not, right? Because these forces are acting in diagonals, right? And so the great way to do it is just, for now, just find out which way the forces are acting. We know this Q is acting on this Q from this direction, right? And we know that this Q is acting on this Q in this direction. And we know that this Q is acting on this Q in this direction. And this Q is acting on this Q, acting on this Q and this Q in this direction. So this is actually the opposite. This is actually the greatest amount of charge. Not charge. Forget what I said. The greatest net force on this positive Q right here. So what's actually the answer? Well, let's think about it, right? No, I have to destroy this beautiful square. Right? Let's say I had that same... No, where's... My black. My pretty black. Okay, this is where force is going to be. We have Q. Sorry, I should probably have brought this down so you can see it. Right? And this is a charged positive Q. Right? So let's say I had it this way. This is the answer, and I'll show you why. Which way is the force acting on this Q to this Q? Now how about this Q to this Q? Since they're the same charge, these forces cancel out. Right? Because let's say I tilted my entire thing, right? A great way to do this is tilt it. Oh, crap. You know what? Here, I'll tilt it for you this way. Tilt it. If you want to see why direction is the way it is, if you just tilt it and you establish that this is positive, this is negative. Sorry, that was horrible drawing. If we say this is positive and this is negative, right, and they're both the same force, same value of force, they're going to cancel out. That's all it is. They're going to cancel out. So let's do... Now let's change it back. Same goes for this way, right? If we know that... Oh no, where's my charges go? Oh, just draw them again. This is Q negative, Q negative. If we know that this force acts in this direction, right? Because it's attracted to this, which is a negative force, and this force acts in this direction, they also cancel out. Because we can also establish that this way, positive, this way is negative. And since they're the same magnitude of charge, they're going to be the same exact force. These also cancel out. So the net force would just be 0. Now, I'm going to stop it from there because I'm going to sleep. If you look at my time, it's 1:36 p.m. 11:36 p.m. And honestly, this was a great exercise. This is a problem where, you know, you're going to have... What would be crazy is if these were not the same chart. Let's say this was 4Q, 3Q, 2Q, and just Q, right? The force would be negative, right? Because... Well, the net force would not be negative because what you have another force acting this way that's a little larger than this one, so it's not going to cancel out the same. So it's a tough question. It's a tough question for sure. But it's doable. I just don't want to do it right now because I'm pretty sleepy. So hopefully you guys enjoyed this session. I think this is my first time, and please like. And actually. I hope you learned something today. That's all I want. I hope you learned something new today. And if there's anything wrong, please feel free to reach out, comment, and like, share, and subscribe. Thank you very much. Have a good day.